Hello and welcome to the video presentation for Module 16. This is our introduction to something called pitch class sets. So in this video we'll work on our definition of what a pitch class set is. We'll work on identifying pitch class sets using letter names and also integer notation. And we will work on determining the normal order of a pitch class set. Then we'll learn how to apply different operations to those pitch class sets, such as transposition and also inversion. Okay, let's talk about a little bit about why these things are important. And we have to kind of talk a little bit about what analysis in music is, and then specifically what it means or what it requires to analyze atonal music, music that does not have a tonal center. So one of the goals of analysis is to demonstrate a relationship between different musical objects and a work, right? So you might be looking at two different sections. They may have similar chords, or the fact that we identify certain chords as being major and other chords as being minor is a relationship, right? So if two chords sound the same, they both sound major, they have a relationship, right? If they sound different, then they have a different kind of relationship. They're different from each other, right? Melodies can be based on scales, and if two melodies are based on the same scale, they have a certain relationship with each other. If they're based on different scales, they have a different kind of relationship with each other. So when we're talking about analysis at its most fundamental level, that's really what we're talking about. We're comparing two different musical things, right? Musical objects, musical structures, chords, scales, whatever, and we're determining if they have some kind of relationship. And in tonal music, right, we can say they're major, minor, whatever. But in atonal music, we don't have that kind of vocabulary because all the stuff we've been learning doesn't really apply to this music, since this music doesn't have major chords, doesn't have a key center. So all of those relationships we've learned are basically kind of useless, right? So we need new tools to describe what's actually happening in these chords, to describe the musical content and compare the musical content of something to something else. And so this pitch class set theory attempts to do that. And a pitch class set is just a way of describing the pitch content of a chord, a melody, or some other musical object in atonal music. And so you can consider these two atonal chords, right? So I'll just kind of play these. Pretty compelling stuff there. But if we counted these in a piece of music, right, how would we describe these? Well, they're not major, right? They're not diminished. They're not seventh chords. They're not polychords. They're not tertian harmonies or chordal harmonies or anything that we've learned about, right, that have a reference to some kind of tonal system. So we don't really have the language to describe what's happening in these two chords, okay? So one of the fundamental uses of a pitch class set is simply to label the pitches that are being used in something like this, like these chords. So at its most fundamental, what we could do is we could say, well, that first chord has a B natural, a B flat, and a D. Okay, great. So that's a pitch class set. We've identified the notes in that musical object, in that chord, right? And that is important, right? We've noted it's something that happens, and this is what's in it. So at its most fundamental, that's what a pitch class set is. For that second chord, you're just saying, well, this has a D sharp, a B, and a C. Okay, great. So at its most fundamental, all we're doing is labeling the content of something in the music. Now, it could be a chord, right? It could be a melody like this, right? So we could use a pitch class set to label what's happening in this atonal melody. Right? Because again, we can't say that's major. We can't say that's minor. We can't say that's octatonic or whatever, all those other things we've been learning about, right? All we can really say is, well, it's made up of an A, an F, an E, A flat, G, and B. Okay. So we've labeled it. We've said that it contains this musical information. And so at the most fundamental level, that's what a pitch class set is doing. It's telling you what the pitch information is of something you've identified as important in the music, so that you can take the next step and compare that to something else. And so there's two different ways of kind of doing this, and the simplest way is what we did, where we notate these as a letter, right? So in that first chord, we said it has a B, B flat, and a D. So the pitch class set, we could just write as B, B flat, D. And we put it in parentheses, and we just write out the names of the pitches, separated by a comma. But you can also use integers to label these too. And when you use integers, you're actually taking the next step where you can now go from simply telling me what's in the chord to being able to compare that to other chords. And so the integers that we use in this book, there's other ways of doing this too, is that C, the note C, will always equal 0. And then as you go up a half step from C, you use the next number up. So a C sharp would be labeled as a 1. And then a D, since that's 2 half steps away from C, would be labeled with the number 2. And this would keep going until you got up to our last unique pitch, our last what the book calls pitch class, which is B, or C flat, which we would then call 11. And then once you get back to C, then you're back to 0. So everything is numbered according to how many half steps away from the note C it is. So if we converted this pitch class set from B, B flat to D into integers, we would say it's 11 because 11 is B, right? 10 because 10 is B flat, and then 2 because D is 2. Okay, so that's a more useful way of labeling them with the numbers, and we'll see why in a second. Okay, so now we need to talk about how we actually go that step further and put these into something that we can use to compare to other things in the music that we're looking at. So a pitch class set is really going to be limited to a simple description. So you're really just telling me what's in that one chord, unless we can take what's in that set and put it into a standard form, which can be compared to other sets. So like when we're talking about a C major chord versus an A major chord, right? The fundamental thing that they have in common is major, because we've decided that a major chord, is a thing that goes beyond, just being C major or just being A major or D major, right? Major is something that's separate from whatever note it's built on. And that's kind of what we're doing with this. We're taking these into a form and we're saying that, well, this is an interval configuration that's independent of what notes it's built on, okay? And so this kind of begins by putting the pitches into what we call the normal order for a pitch class set. And so the normal order is the most compact version of a set. Putting a set into normal order is similar to putting like a triad in root position. So we think of, a first inversion major chord and a second inversion major chord and a root position major chord as all kind of being the same thing. They're, again, that kind of second level, that above thing, right, that we call a major chord. So even though they're made out of different intervals, right, so a root position major chord would have a third and a fifth, but in first inversion, that would be a third and a sixth, but in second inversion, that's a sixth and a fourth. So those are all different intervals, but we still consider them to be the same thing, because we know that if we reduce it, it becomes a root position chord, no matter what the other intervals are. So we're kind of doing the same thing when we're putting these pitch class sets into a normal order. We're creating the most compact version, the most universal version of this. Okay, so the first step in figuring out the normal order is to write all of the possible ascending orderings of the pitches in your set within an octave. So here's our set again, 11, 10, 12, which as a reminder was just B, B flat, D. And I'm going to reduce all of these to an octave, and there's only ever going to be a number of possibilities equal to the number of pitches in your pitch class set, right? So there are 3 pitches in this set, so there are only 3 ways we can do this. And they're going to be, okay, we'll start on each note, put everything within an octave. So if we start on 11, on the B, we get our first set there, right? Which is the 11 to 10. If we start on the D, the number 2 there, we get that set 2, 10, 11. And then finally, if we start on the B flat, we get 10, 11, 2. And the normal order, the one that we care about, the one that's the most fundamental, the most basic, right? The most basic form of this is going to be that last one, because that is the one that creates the smallest interval between the first note and the last note of that ascending set. So since B flat to D is a major third, and everything, all the other orders we tried were bigger than that major third, then that last one, since that's the most compact version, is our normal order. Now, there are cases where, and it's pretty common actually, where things will be ties, and the book talks about how to break those ties, and it comes down to, well, if you have two ascending orders that are tied, then you look at the second biggest, or the second most wide interval, right? So you look at the first note and then the second to last note, and then you compare those. And if there's a further tie, you keep going, and if they're all tied, then you end up taking the order which has the lowest number, right? The number based on that half-step conversion we were talking about. So look to the book to talk about that, but there will often be ties, and that's how you break them. Okay. So what's really important with this stuff is the different operations you can do once you have the pitch class set into a normal order, and once you've kind of accepted it as a thing, as an object. So just like in tonal music, it's possible to transpose or invert a pitch class set, right? So we just kind of talked about how a C major triad and an A major triad are both major, right? And we know that because we can take all the notes in a C major triad and transpose them so they start on A, and we'll get something that is related, something that's similar. In atonal theory, it's the same kind of thing. You're taking a pitch class set and you're applying a transposition, and because you know that they're related by transposition, you know that those two pitch class sets are related, right? They have some kind of relationship to each other. And in atonal theory, we've taken it kind of a further step, and we've made them into mathematical operations. Okay, so for transposition, we use the symbol T with a little n subscript to indicate how far you're going. And all this means is to add a number of half steps, which is n, to each pitch in the set. Okay, obviously this is done with the integers, not the letters. For inversion, we're going to subtract each pitch from the octave, which is 12, and then apply any transposition that might be indicated by that. And now that inversion, for some reason, which I don't actually know, is a compound operation. I'm sure there's a really good reason for it, but I don't know what it is. So it will always be accompanied with that transposition. So we'll see that in a second. All right, so let's talk about the actual math with this, which can be a little bit confusing, but it kind of comes down to the fact that in our system, there are 12 unique pitches, right? And we've decided with our conversion that we're going to label the first pitch 0 and the last pitch 12. So what we do is we use something called modulo 12 arithmetic. And all that really means is that we're saying the maximum number we can have is 11, and the first number we can have is 0, because that gives us 12 numbers, right? It's almost like a clock, right? So if we say something like, well, it's 10 o'clock now, how long do I have until 1 o'clock, right? You don't actually subtract 10 from 1 and get the result, right? What you do is you kind of count up till you get to 12 and then restart with 0, and then you end up with your number of hours, right? It's really the same kind of thing with this, and actually it's the same operation because we're using 12 with this as well. So basically what you do is any result of an operation that is 12 or larger, you subtract 12 from that result until the number becomes 0 to 11, anywhere from 0 to 11. So you're reducing anything that's 12 or larger so that it is 0 or 11. And that is kind of the quickest explanation of what this is, right? Basically, once we get to 12, we're just resetting that to 0. And that's it. Okay, so some examples of this kind of math. So if we do 7 plus 7, that gives us 14. But if we did 7 plus 7 modulo 12, right, then 12 is the highest we can go before resetting. So what we do is we take that 14, subtract it from 12, and we end up with 2. So in modulo 12, 7 plus 7 is not 14, it's actually 2. Okay. Something like this, 5 plus 7, would normally give us 12, but in modulo 12 operations, right, in modulo 12 arithmetic, that would give us 0, because once we get to 12, we reset to 0. Something like 1 plus 6 would give us 7 in normal arithmetic, and in modulo 12, it would also give us 7, because that's not larger than 7. We don't have to reset because we're not going over 12. Okay. And again, the reason this has to happen is because we think that all the notes, all the C's are the same, right? All the D's are the same. So we have octave equivalents, and we have 12 notes. So we're basically reducing everything to be within the 12 notes that we are familiar with. And that's why this is modulo 12. Okay. So let's talk about the transposition operation. So to transpose a set, you just add n, keeping in mind it's modulo 12, to every pitch in the set. So if we're going to transpose our set, our 10, 11, 2 set, 2 half steps, right, which would be a whole step, what we're going to do is we're going to add the number 2, modulo 12, to each of those numbers, and that will give us our transposition. So starting with our 10, 11, 2, we add 2 to each of those numbers, we would get 12, because 10 plus 2 is 12, 11 plus 2 is 13, and then 2 plus 2 is 4. So our initial results, by adding 2 to each one of those pitches, adding a whole step to each one of those pitches, is 12, 13, 4. But remember, we don't really want anything higher than 12, right? We have to reset when we get to 12, because we have to keep this within the 12 pitches that are available, right? There's no 13th pitch, okay? And the 12th pitch is just an octave, so we reduce that to be the original pitch. So we just subtract 12 from anything that's larger or equal to 12. So that first one, 12, becomes 0, right? It's like octave becomes unison, basically. That 13 becomes 1, and that 4 can stay the same. So when we finish our transposition, we'll write T2, right, transposition 2, of 10, 11, 2 is equal to 0, 1, 4. And if we made this musical, which is what this should be, right, this is basically like saying, okay, B flat, B, D is what we start with. And we're going to transpose all those notes up a whole step. So we get C, C sharp, E. And you'll see that B flat up a whole step is C, B up a whole step is C sharp, D up a whole step is E, and we just use numbers to get there instead of knowing our half steps and whole steps. Okay. Now we'll say that these two sets are equivalent, right, are equal to each other through transposition. So now we've shown that those two sets have some kind of relationship to each other, right? We've accepted the fact that they have the same interval structure, right, that we've manipulated through transposition. So we can compare them. We can say, well, those two things are related by transposition, which is significant in our analysis. Okay, one more operation, which is the inversion operation. And this is a little bit different than, well, it starts out the same, but it ends up being kind of interestingly different when you compare it to tonal inversion. So with the inversion operation, we're going to subtract, keeping mod 12 in mind, each pitch in the set from the octave, which is 12. Okay, so if we're going to do the inversion of 10, 11, 2 set, right, we're going to start with our 10, 11, 2, but we're going to subtract that from 12 this time. So 10 from 12 gives us 2, 11 from 12 gives us 1, and 2 from 12 gives us 10. There's nothing over or equal to 12, so we don't have to worry about that for this. So our results from inverting this are 2, 1, and 10, right? And so if we thought about the intervals, that would actually be the intervals that we would normally get through transposition. But you'll notice that now it's not in its normal form, right? So it's not even in its ascending form. So what we have to do is after we do the inversion, we have to convert that back to its normal form. And so we could write it out, but for now, we'll just say that my normal order for this wouldn't be 2, 1, 10. It would in fact be 10, 1, 2, because that's the most compact version of that set. So the real result would be 10, 1, 2, not 2, 1, 10. So we say that through our transposition 0 inversion, which is what we did, we now have this set 10, 1, 2, which is equal through inversion to that original set. All right, now, like I said, for some reason, the transposition operation would be applied after this because this is like a compound operation for some reason. I don't know why. But what we did is we did T0, which means transpose 0. So we're not transposing it. We're just inverting it. Okay. Now, one thing to notice when we look at the actual notes that resulted, again, we had our B flat, B, D original set. And when we inverted it, it became B flat, C sharp, D. So it's not like that half step, right? That half step became a seventh, right? And that B to D did not become a major sixth, right? It's not a standard, it's not what we expected from what we know about inversion, right? And that's because we had to reduce it to its normal order. We had to get rid of that, of the stuff that would be, well, we had to compact it, right? We had to reduce everything so it was smaller. And that created this interesting effect, which is when you look at the first interval set, it is a minor second to a minor third, but when we inverted it, now it's a minor third to a minor second. So we get a reflection of what we had before. And that's interesting about atonal inversion, which is you don't end up with, you know, our traditional inversion, which is, you know, major third becomes minor sixth. What you end up with is you flip the order of the intervals. And that brings up something pretty cool, which is what happens when we invert something like this familiar quote unquote set, right? So here we have T7I on 0, 4, 7, right? So transposing up 7 half steps, but we're also going to invert it, right? And the 7 is kind of arbitrary to this. My point would be proven either way, but I'm just going to do this and you'll see why. So we're going to start with this set, which is 0, 4, 7. Now, this is a pretty familiar one, which is C, E, G. It's a major triad. So let's see what happens when we invert a major triad, right? Normally when we invert it, in tonal thinking, we would get a first inversion triad, right? Or a second inversion triad. But let's see what happens when we stick to this operation. So going with the numbers, to invert this, right, we subtract all these from 12 and we end up with 12, 8, 5. Okay, modulo this time, so we end up with 0, 8, 5, right? Now we also want to transpose it, so we're going to add 7 to each of these numbers. So 7 plus 0 is 7, 7 plus 8 is 15, 7 plus 5 is 12. So when we do our modulo, we end up with 730, and that is no longer our normal order. So to put that in normal order, we end up with 037. So now we've proven that 047 is equal through inversion to 037. And if we look at what 037 is with notes, we'll see that it is in fact a C minor triad. So through this kind of thinking, we've proven that a major triad, you know, which is major third, minor third, is related through inversion to a minor triad, minor third, major third, which is pretty interesting. And, you know, it kind of proves that, you know, in tonal thinking, there are these relationships that we're not aware of because we're so concerned with that center pitch, right? But if you really think about the interval content of a major chord and you divorce it from its tonal context, right? From what we expect it to be, from what we're used to it being, we'll notice that the interval content, if we're just talking about that, right, is actually equal to a minor triad. But in our normal thinking and tonal thinking, right, major and minor triads are not the same thing. But if you look at it this way, they in fact are, which I think is pretty interesting. Okay, great. Well, that is a good introduction to set theory. Hope you enjoyed it. and we'll be doing more exercises in our class meeting. And have a great day.